Today we're going to be talking about factors and greatest common factors. And one of the first things we need to talk about is a prime number. So just to review, because I know you have dealt with prime numbers earlier in the year, a prime number is bigger than 1 and can be divided I'll rewrite this in, and can be divided only by 1 and itself. Let's see if we can fix this. There we go. There. Okay, so what we're going to do is use prime factorization. We're going to make a factor tree, in other words. So let's do the prime factorization of 40. So we want two numbers that multiply to give us 40, such as 8 times 5. Don't use anything that's got a factor of 1 in it. You ask yourself, are either of those numbers prime? Yes, 5 is prime, so circle it. Now break down the 8. 8 is equal to 4 times 2. 2 is prime. It can only be divided by 1 and 2, so circle it. Break down the 4. It's 2 times 2. Both of those are prime. They can only be divided by 2 and 1. So our prime factorization is, because we have 3 2's, we're going to have 2 to the third times our last circled number, which is 5. As soon as you have circles on the end of all your branches, you have finished your prime factorization. And 2 to the third times 5 is indeed 40. Now we're going to do the same thing with 33. 33 is equal to 3 times 11. Now both 3 and 11 are prime, so we'll circle them. And the prime factorization of 33 is 3 times 11. Now we want to find the greatest common factor of each pair of numbers. Now this is the largest number that will divide into both of them. Okay, so 12 and 16. The largest number that will go into both 12 and 16 is 4. So the GCF is 4. The largest number that will divide into both 15 and 25 is 5. So the GCF is 5. So now let's find the GCF of each pair of monomials. So we're going to take each part separately. The GCF of 18 and 27 is 9. That's the largest number that will go into both. Now, when you're dealing with variables that have the same base, take the one with the smaller exponent. Okay, so I'm going to say use the one with the smaller exponent. So we have q to the second and q to the third. The one with the smaller exponent is q to the second. Now, of course, this is only when we have the same base. These have the same base. These are both q's. Now let's look at this next one. The GCF of 16 and 96 is 16. That's the largest number that will go into both of those. Well, 16a to the 6 has a part with an a, but 96 doesn't. So we cannot have an a in our GCF, so we're just going to leave it as 16. That variable would need to be present in both in order for it to be part of the GCF. Now let's look at this next one. The GCF of 8 and 7 is 1. That's the only number that will go into both. The GCF of x and b to the second, there isn't one because they don't have the same base. So it's just 1. They would both have to be x's or both be v's in order to be part of the GCF. The GCF of 15, x to the third, and 9x squared. The GCF of 15 and 9 is 3. The bases are the same on the x's, so we're going to choose the one with a smaller exponent, which is x squared. So the GCF is 3x squared. Now, 8x squared and 7y to the third. The GCF of 8 and 7 is 1. Of x squared and y to the third, they don't have the same base, so it's not going to be part of the GCF. So the GCF is just 1. And that's it for factors today. Thank you very much for joining me.